Hello viewers, welcome to EF. Today is the 12th video of Complexity Theory of IT Security course. In this video, I would like to discuss about what is the reducibility and then the proof of reducibility. So let's see the formal definition of reducibility. Reducibility or polynomial reducibility. So let's say L1 is a subset of sigma 1 star and L2 is a subset of sigma 2 star, and both are two languages, or you can say two decision problem. Now L1 is called polynomially reducible to L2 if there is a function that maps the input sigma 1 star, which is the input from a machine, to the another machine sigma 2 star, which is the input from another machine, such that there exists a deterministic Turing machine Tm with initial state of x input. After a static many steps, the deterministic Turing machine will go to output f of x and final state, where for all of x which belongs to sigma 1 star, and we have the Turing machine for input size n is equals to polynomial time complexity, which is order of n to the power k, and k is some natural number. The second condition is for all x in sigma 1 star, we have x in L1 if and only if x function of x is in L2. Here is a note that L1 can be polynomially reducible to L2, and there is an algorithm. If there is an algorithm for if there is an algorithm or deterministic Turing machine for L2 in polynomial term, then it is also possible to construct another deterministic Turing machine that can decide the L1 in polynomial time. So how can we do it? In this figure you can see that we have two machines. The first machine is DTM1 for F, and the second machine is deterministic Turing machine TM for L2. And finally we write a new deterministic Turing machine that decides L1. So now let's see how it works. At the first step, it will say that we have a deterministic Turing machine which maps the sigma star input and gives the output sigma star 2, where sigma star 2 has the function of x, and the deterministic Turing machine M prime will finally decide L1. So now the main part is, at the very beginning we have two different machines, the M and M double prime. So M takes the input x and it gives the output function of x in polynomial time order of nk, and the M2 is another different machine which will take the input function of x and gives the output yes or no in polynomial time. Now once I will use this x input into my machine M, and it will give output f of x, it will not go to the final state yes. Instead of going it to the final state yes, it will be initiated as input for the deterministic Turing machine T of M double prime, and then it will produce output yes or no for the input of x. In that case, it will create another new machine which will produce the m prime, and that will decide for L1. So that I was also writing here, that then now we have this m solves input x with the given solution f of x, and it takes complexity order of nk, and m prime machine takes the input f of x which belongs to sigma 2 and gives the output yes or no. Now the machine m, instead of going to yes final state, it takes the output, it gives the output, and it is going to the initiate at the second machine m2, and m2 is just giving the output yes or no for the input of x machine, and we are designing the new machine m prime that gives the output yes or no. Now the question is, what is the time complexity? The time complexity for this case is Tm has input n, then the polynomial time complexity is order of nk. Tm double prime has the input size n. For that, f of x, because f of x is come from x, and it has also the time complexity order of n. Now question is, what will be the time complexity for the machine m prime? Before that, we should know that the consequences are not about the m2 is in polynomial time solvable. It is about, if I have a good machine for m2, then I can construct a good machine and useful machine for m1 also. That is basically say about the polynomial reducibility. What it means, now let's say we have a machine m which will take the input language L1, and gives like we have the Turing machine M, and where the Turing machine M1 will produce output in exponential time, where M2 has separately give a polynomial time complexity for a polynomial time. But finally, when we are going to construct a machine T of M prime, then it will be also exponential. So because the input is depending on the number of size of n, what is the size we are giving as input to my first machine, I will get the output depending on that machine only. So that is the exceptional case. So our case, we have the input size n and input size n. So for Turing machine M will have order of nk polynomial time complexity. Now for function of x is output of Turing machine M, which we gives output for the machine Tm of n. So let's say this output will have the order of n to the power k of 1. Now if we connect and design new machine Tm prime, for the new machine we will have a polynomial time complexity order of n to the power k to the power k1. No matter, finally it will be a polynomial time complexity for m1 machine also for speed up. Now if we want to really calculate the complexity of the Turing machine of M prime, then we need to have some deep mathematical calculation. I am not discussing that in here. So normally we can say that final machine of T of M prime will have the polynomial time complexity, as we have the polynomial size input. Thank you for watching this video. In next video I would like to discuss about different NP complete problems and their NP completeness proof.